Good morning. This is Brent McKee, and I wanted to share some of the work we've done in the past year in Falls Lake. The bigger picture overview is that reservoirs have garnered a lot of attention in recent years as potential sinks for atmospheric CO2 and major carbon storage sites. However, this hypothesis has not been rigorously tested, and certainly there are very little quantitative data to back that up. And so that's the driving force behind this presentation in this study. The title of my talk today is Evaluating the Importance of Reservoirs as Organic Carbon Sinks and Their Role in Climate Change. I want to point out the folks here on the bottom line. They are indeed the bottom line through a very challenging past year. They have helped collect samples when it was very difficult. They've done analyses in the lab when it's almost impossible to do analyses the way we normally do based on COVID protocols. And through it all, they pushed through and very successfully. There's a subtitle to our talk today, and that is, when and where do particulate materials enter Falls Lake, and what is their fate within the reservoir? There are a couple of objectives here. One has to do with the inputs of particulate material to Falls Lake, and the second one has to do with the fate of materials within Falls Lake in the sediments. The first objective is to quantify the temporal and spatial inputs of suspended sediments and associated organic carbon at tributaries into Falls Lake. And the second is to collect cores within the lake to quantify rates of bottom sediment mixing and accumulation. These important process parameters, mixing and accumulation, are needed to quantify carbon and nutrient fluxes in bottom sediments. So to achieve the first objective, we identified 4 tributaries and we set up collection stations at each one of these that are near USGS sites that measure water discharge. So Flat Creek, Eno River, Little River, Ellery Creek, they add up to be about 70% of the water discharge into the lake and all into the upper part of the lake. So we set up rating curves for discharge versus parameters like total suspended matter here by going out and measuring total suspended matter and then noting the discharge from the USGS at the time in which we collected them. And so in some cases like Ellery Creek and Little River, there is a sort of a linear response to discharge in total suspended matter. And in these larger tributaries like Flat River and Eno River, it's a more of a logarithmic approach to a plateau. And the R-squares for all of these are between 0.8 and 0.9, so pretty good relationship. We also established rating curves for particulate organic carbon in micrograms per liter. And again, there seems to be more of a logarithmic increase in particulate carbon entering the lake as discharge increases at all of these sites. And again, our values between 0.7 and 0.9. So relatively good coherent values. So there's also a good relationship between total suspended matter and particulate organic carbon. And we think that's because most of the carbon coming into the lake, upper lake, comes along with lithogenic materials that make up most of the total suspended matter. All of these rating curves can be compared to watershed simulations. So they have an additional value that could be interesting. It's turned to the second objective, the fate of particulate matter in Falls Lake sediments. We all know that CO2 emissions to the atmosphere have increased dramatically during the past decades. But if carbon accumulation in reservoirs is an effective carbon sequestration strategy, then the storage of organic carbon must also increase substantially over time. So that can be tested. The question is, how have the sediments and carbon accumulation rates changed over the lifetime of the reservoir? So more specific questions aimed at Falls Lake: what are the sediment accumulation rates in Falls Lake? What is the relationship between sediment accumulation and carbon accumulation? And how do carbon accumulation rates vary over the past few decades? Do they indeed increase? So to achieve this objective, we took cores down the length of Falls Lake from the upper part down to near the dam and we collected these cores and dissected them and analyzed each centimeter. For brevity, I'm only going to show you number 2 and number 9 representing the upper and lower part of the lake. So we use lead-210 to establish our geochronologies, and it's a naturally occurring radioisotope that is supplied from the atmosphere. It has a 22-year half-life, and you can see from station 2 and station 9, there's a gradual decrease of excess lead-210 with depth, which indicates both burial and decay. So we have a time frame. Station 9 shows a little bit more dynamic profile, which turns out to be pretty interesting. So we can use these lead-210 geochronologies to put together a framework, a time framework over the last decades to look at all kinds of things. This shows the sediment accumulation rates and how they've increased over the past few decades. There's a peak here that 2019 may have something to do with Florence. We'll look into that more. Here's the carbon accumulation rate from station 9, showing a pretty dramatic increase in the organic carbon accumulation here, though lots of character to the profile, and so some interesting things to investigate. I want to point out that these values between 300 and 400 and even 500 grams carbon per meter squared per year of organic carbon accumulation rivals any blue carbon environment like salt marshes and seagrasses that are noted to be burial sites for organic carbon. These rates should provide a useful insight to lake simulations and help with sediment diagenesis models. So in summary, the tributary rating curves can provide good estimates of sediment and carbon input to the lake using readily available water discharge data from the USGS. And secondly, geochronologies established in the lake enable us to evaluate rates of both carbon and sediment accumulation, and also can provide a temporal framework to evaluate the timing and fate of other particulate materials of interest, things that enter the lake, such as nutrients, microplastics, and contaminants. Thank you.